So now we're into part 3. At the end of the last one, we had determined our coefficient of performance, our mass flow rate, which we need to put up on here, and we'll put a couple more input variables in here to have everything showing up on this diagram and they're nice and neat. One thing we need to do is convert these, well, not convert these, but edit these. Right now they're showing up, but they won't in a moment if we don't do something, and that is make them so they show up all the time, not just after calculations. Otherwise, we end up wondering where they went sometimes. All right, so there we go. Looking good. We had a program over here. What we want to do is take this 24,000 BTUs per hour. We're going to turn that into a variable. We're going to call that Q dot evap. So that's the rate of heat transfer to BTUs per hour from the evaporator, divided by the specific BTUs per pound flowing through the evaporator will give us our mass flow rate of pounds per hour. So we change that, and we'll come back over here, and we'll just go back to the edit mode. And the easiest thing to do sometimes is copy one of these, move a little bit, and edit it. And let's see if our Q dot showed up yet. So no. So we edited over here, but we really didn't tell the program to check anything yet. So it still thinks we're in edit mode. So the easiest thing we can do is look at the formatted equations, and we can see that it took care of that. Now just to show you what happens, if we go to calculate right now, we're going to get an error because we don't have a numerical value for that. We don't have enough information to solve that equation. And we've got 20 equations, 25 variables with 4. So we've got 25 variables but only 24 equations. So we need 25 equations for 25 unknowns. So we get out of that, and T4 is put in the diagram in more than one place. Okay. And it is. That's the other issue, because I didn't edit it because I couldn't. So now we can. We'll go back to the edit mode, and we'll get rid of both of those problems. So Q dot evap is now what we want. Got that. And we'll line these guys back up again. And alignment features, left sides, space evenly, makes it look nice and neat. Let's go ahead and put an output variable. So what else we want to do is we want this to be in tons. So we're going to call that tons. And that's actually a refrigeration unit as well as a mass unit. Depends on the context. He knows what you're doing with it. Wrong button. I want Q dot. It's going to be BTUs per hour. Okay. And alternate units are going to be ton. Okay. So, but I want this guy to be the alternate unit. It's going to input how many tons, but then I'm going to have it show me as an output. So let me go ahead and just duplicate that. Control C, Control V, and edit that, and we'll call it the same thing, but we're just going to show the regular units, and then we're going to put it back into the green color for some of our output variables. And we're going to call it an output variable. And we want it to be show units. There we go. That's going to be BTUs per hour. Now, what else we want to do is put the actual value in. Oh, we want to put one more output variable in. We want our mass flow rate on this page. So let's go ahead and get m dot. That's good. So m dot, we'll move up over here. Q dot in BTUs per hour, we'll put down here. We're getting a little scrunched up over here. Well, we can move these a little bit. Let's move these a little bit. And once we get rid of this with a simple 2, that'll clear up some space. All right, so now back to the data entry mode. Call that 2 tons. Put a tab out of that. And why is this doing that? All right, let's calculate. Oh, that's why. It's supposed to be BTUs per hour. I need to edit the alternate units. I have BTUs per hour. Q dot evap. Okay. Oh, there we go. That's right. 24,000. BTUs per pound. Looking good. And we can look back at our array if we want to. None of those have changed. But now we've got additional information. We've got coefficient of performance. We've got mass flow rate for a 2-ton system. So one other thing we can do, stretch that out a little bit. More this way. All right. Now, that's for R12. What if we wanted to look at other items, other refrigerants? So there what we can do is we can put in here a string variable, and we're going to call it $. So a $sign after a sequence indicates it's a string variable. So $$ is our refrigerant. We're going to say, actually we're not going to do it that way. We're going to, every place there's R12, we're going to do a global find, Control F, and that's not what we want. We want a global replace, Control R, find R12, replace with $. So I usually only do individual replacements just because every once in a while something weird is happening and you replace something you don't want to, particularly if you're just dealing with numbers. If you want to replace all the numbers 2, well, it's going to find the 2 in a 12 and replace it. So we replaced all of those. Now that's done. Now it's not going to work. Okay, so calculate. We don't know what our, so we got 20 plus 5. We don't know what the R value is. So we don't want to debug because we know what we did. And what we want to do is create a string variable list. And we want an input variable. And the input variable, we need to go to new variable. Uh-oh. There we go. New string variable. And name is our $. Okay. And we need a string list. So let's put in R12, R134A, R717, that's water, and R1234Y. Alright, F, see if that'll work. So, click OK. This is an input variable, so we'll make it red. And for some reason, I lost my darken mode. I like it darker. All right. Okay. So R12. Go back to D. So right now, we're using R12, so nothing should change. Our should calculate fine. Everything is the same. Our array variables should be the same. Looking good. Now, what if we go to 134A, a drop-in replacement for R12? What happens? Things change. Look at that. So we kept everything, all these constant. All we changed was the working fluid. We still wanted to get 24,000 BTUs per hour out. Our temperatures and pressures we kept the same. Coefficient of performance changed. How much did it change? 3.262. A little bit higher coefficient of performance. How about our mass flow rate? A little bit lower mass flow rate. You can see there's differences all the way around the cycle. That's great. 1717, we can check that. Way lower mass flow rate. Why? Because we've got much higher latent heat of vaporization. So we're going to get higher values per pound on these. R717 is ammonia. So let's see if 1234YF. I haven't tried 1234YF before, and it works. And you can see what's happening. Mass flow rate's back up 500 something. Coefficient performance 0.0381, and so on. But that's great. But what if we want to compare them side by side? You can't really do that this way. So what we need to do is do this as a parametric.